Hi guys, so I'm going to do a quick video introduction to series and Sigma notation. This way you have some prior knowledge before we get into the Sigma notation for this unit. So a series has a connection to our sequences, where a series is just the sum of the term values in a sequence. So we're going to still deal with our sequences, but now we're going to start adding up those term values. Just a side note, you'll talk about this more in detail when you get to pre-calculus and calculus and future math courses, but you'll start talking about series that diverge, which means they continue to grow. There's no number that they approach. However, some will converge, and what that means is as you keep adding up these term values, the sum will approach a certain value. So again, that's just a little heads up that you'll be seeing that when you get to pre-calc and calculus. So an example of a series would be given this sequence of 10, 14, 18, 22, and then this being the rule that generates all n values for n plus 6. The series would just be the sum of those values. So 10 plus 14 plus 18 plus 22 plus ... So the next one would be 26. And so we just continue to add the term values. This would be an example of one that diverges, because as you add more of these numbers are getting bigger, and so it'll never approach a certain value because you're just adding more and more each time. But we can talk about partial sums, and so we use the notation S sub n. And so S sub n is the sum of the first n terms of a series. So it's really important that we pay attention to what our subscript is. It's going to tell us that we're just going to add up the first n number of terms. So some examples of that using our series above. Find S1. This tells us to find the sum of the first term. And so that answer is just 10. No tricks there. Find S sub 2. This tells me I'm going to add up the first two terms of this series. And so that's 10 plus 14, and I get 24. So that's the sum of the first two terms. And find S sub 10. This tells me that we're going to add up the first 10 terms of this series. And so that's 10 plus 14 plus 18 plus 22 plus 26 plus 30 plus 34 plus 38 plus 42 plus 46. So this is the first 10 terms of this sequence, of this series. I'm going to add those up. I didn't actually add those up, but we will learn a way to get the total quickly so that we don't have to sit there and add up all these values, especially because what if you needed to find S1000, right? We don't want to add up all those digits, so we're going to find a way to actually add them up in a much quicker, precise way. But we're also going to take this and we're going to learn how to write this in a new notation, and that's where the sigma notation comes into play. And so we introduce this Greek letter sigma. It's kind of this weird E again, but it's a shorthand to find the sum. So this means the sum of some values, and so it's following the same rule. So if I said S sub 10 for our series from the previous slide, I can rewrite it using the sigma notation. So again, the sigma tells us that we're adding, and then there's three components to it. You have these two indices at the bottom and the top, and then you have the rule, what we're adding. So what this is going to tell us, and I'll explain a little bit more in the next slide, is this tells us our start. So I'm going to plug in a 1 for n, and I get 10. Plus, then I plug in a 2 for n, and I get 14. Then I plug in a 3, and I get 18. And I'm going to continue to do this until I get to this top number. So when I plug in the 10, I get my 46. And so I generated that series using the Sigma notation. Again, it's a shorthand for what we did right here. Right? So we're going to make that connection between the partial sums and Sigma notation. So let's take a little closer look to the parts of Sigma notation. Again, you'll see more of this in pre-calculus and calculus. Ignore this down here for right now. We'll come back to that. So the 3 components to your Sigma notation is at the bottom, this tells us your start value. So this is telling me that I'm going to start when n equals I. I don't know what I is yet, but that's where I'm going to start. The second component is the top. That's where we end. So I'm going to continue counting from I, and I'm going to keep going all the way until I get to j. And I'm just going by my natural number. So I'm going to start at I, then I'm going to add 1, and I'm going to add 2, and then I'm going to add, I'm going to just keep adding 1 to it to get to this value j. A sub n is what we're adding. And so this expression here, right, if I wanted to write this, would be a sub I plus a sub I plus 1 plus a sub I plus 2 plus ... right? And I'm going to go all the way to j. So I can say a sub j minus 1 plus a sub j. So don't stress if this is kind of confusing, but what we need to know is this is where we start, this is where we end. We're going to go up by 1 value each time until we get to our end, and we're going to add up these values. You'll get some practice in the next slide. Looking at the bottom here, just a little sidebar. Different notations can have the same series representation. So I have this series n equals 1 to 10. So we start at 1, work our way up to 10 of 2 to the n. So if I were to write that out real quickly, I would have 2 to the first plus 2 to the second plus 2 to the third plus ... plus 2 to the ninth would be the one before the last one, plus 2 to the 10th. So I'm adding up my powers of 2 from n equals 1 to n equals 10. Now this, even though it looks different, will actually have the same representation in the series. So if I plug in a 0, I will get 2 to the 0 plus 1, which is 1. When I plug in a 1 for n, I get 2 to the second, plus when I plug in a 2 now, I get 2 to the third, plus now if I work 1 behind, so if I go up to 8, I would get 2 to the ninth, and then when I plug in my 9 for where I stop, I get 2 to the 10th. So just a little sidebar, we have to pay attention to the components because different expressions can have the same exact meaning. Here are some examples to expand. I'm going to do the first one. We're not going to actually find the sum. I just want to be able to, be able to read what the Sigma notation tells us. So this first one says I'm going to start at 3, I'm going to end at 6, and the rule I'm adding up is n squared. So I start at 3, so that's 3 squared plus 4 squared plus 5 squared plus 6 squared, and I'm done. So notice the squareds, that should be squared. So notice n is increasing by 1 each step of the way. I started at 3, ended at 6. Pause the video, try the 4 remaining ones, and then when you're done, you can check, see how your answers match up to mine. So hopefully you gave this a shot. So looking at this one, we start at 1, we go to 7 of n plus 1, so that's going to give me a 2 plus 3 plus 4 plus 5 plus 6 plus 7 plus 8. So there's 7 terms. I'm adding 2 plus 3 plus 4 plus 5 plus 6 plus 7 plus 8. For the third example. I'm starting at 1. I'm just adding the first 3 terms from 3 times 2 to the n. So that becomes 3 times 2 to the first plus 3 times 2 squared plus 3 times 2 to the third. And again, that's just the expansion of this. For the fourth one, we start at 4, we end at 7, and we're adding up n over n plus 1. So that will give me 4 over 5 plus 5 over 6 plus 6 over 7 plus 7 over 8. So again, that is the sum of the first 4 terms of that one. Now, this last one, I changed the index here to n equals 0. So let's see what happens when we do that. So I get a over 0 cubed plus a over 1 cubed plus a over 2 cubed plus a over 3 cubed plus a over 4 cubed plus a over 5 cubed. Now, this is the form, however, the issue with this, we can't do this here. So this was really a bad example. We can't divide by 0, and so this series really doesn't make sense, but again, we could rewrite it out in the expanded form. So now we'll look at writing the following in Signma notation, and this is going to require you to be able to find the rule or the explicit formula for each of the sequences that you see. So remember, they're separated by the pluses. And so if I look at this sequence, I notice that I'm subtracting 2 each time. And then I started at -3. And so when I write this in Signma notation, I start at 1, and I have 1, 2, 3, 4, 5, 6 terms. And then I'm going to find the rule that generates this. Well, I start at -3, and I'm going to add -2 times n minus 1 each time. This generates the rules, the terms here. So again, this is our sequence, our explicit rule for the sequence, -3, -5, -7, -9, -11, -13. For the second one, I have s sub 3 equals 8 plus 11 plus 14. And so I know this will equal, starting at 1, going to 3, since I have 3 terms. It looks like I'm going by 3s here, and my start value is 8. So that would be 8 plus 3 times n minus 1. So those are 2 examples of arithmetic. These 2, I believe, are geometric. So if I look at s sub 4, it looks like I'm multiplying by 1/2 each time. And so this would equal 1, 2, I have 4 terms. I'm multiplying 3 times 1/2 to the n minus 1. So again, this is just the explicit rule of this sequence: 3/2, 3/4, 3/8, 3/16. And our last one, I start at 5, and it looks like I'm multiplying by -3. And so I start at 1, I go to 6, and my initial term is 5. I'm multiplying by -3 to the n minus 1. And so, again, we can rewrite from the expanded form to Signma notation, or we can go from Signma notation to expanded. And then where we're heading with this is we're going to be using the Signma notation to find the actual values of partial sums of both the geometric and arithmetic series. They actually break down to simple formulas. And from that, we will also find the sum of an infinite geometric series. This gets interesting because it becomes very theoretical in nature. So that's where we're heading. Thank you for taking the time to watch this, and I'll see you in class.